Okay, so I've chosen these three words, multiscale flow engineering, very carefully because it explains exactly what Jason built and what we've been working on for the past decade. Because the word flow comes from the fact that we're working on computational fluid dynamics in unconventional situations. The word multiscale means because we're trying to span many orders of magnitude of space and time, where there is multiple physics, multiple chemistry, physics, and so on. And engineering is very important because we want our models, our methods to be used by industry and impact engineering applications. And I've come up with a simple example of a ship in a sea, which perhaps is not clear. This is a tanker ship over here. And we work with AkzoNobel who sell coatings, high-performance coatings, in order to either reduce the drag or reduce the bacterial growth which grows on the surface of these ships. And so what they're interested in is a final result. What's the drag reduction? What's the growth of these organisms and so on? So we're talking at a macroscopic scale. So we need a macro model at large scale to be able to understand the overall characteristics of the problem. But the engineering design comes from the what's happening at the surface, and to understand that we need to look at a molecular approach. So we're designing it, let's say, a nanostructured surface, then we need to know what happens when we change the surface, what happens to the overall macroscopic properties. And this is a multiscale problem. You can also have mesoscopic models in between, such as droplets or even bacterial growth and things like that. And the challenge is to be able to link all these models together in one simulation. So we could have at one scale nanometers and femtoseconds at the molecular scale to be able to resolve, millimeters and milliseconds at some mesoscopic model. And we obviously want to be able to predict in hours what the performance of this coating will be, and over meters of scale. So if you do the maths, you quickly realize there are around 10 to 20 orders of magnitude in time and space between the smallest model which you have and the largest model. And so it may not be obvious, and we've heard from Martin in the previous talk, that this is relatively challenging. So how do we do the connections? How do we do the connecting of these models? And I'll start by using time. So the first approach, which is probably more common, is what we call a sequential approach, where we start by running a series of molecular simulations. We gather that data, we put it in a library, or we fit some model, and we use what we've learned from these sequentially, what we've learned from these molecular simulations in some enhanced continuous simulation. If you're an experimentalist, you can do this as well by replacing the molecular simulation with an experiment. So that has advantages and disadvantages. The second approach is called a concurrent, where you have all your models running at the same time, passing information and producing your macroscopic solution at the end of it. So here I've shown two timelines for this concurrent approach. Now, it may not be obvious, but there are advantages and disadvantages of these two techniques, and I have an analogy to describe it. So imagine you're going on a trip, right? And you know exactly where your destination is going to be. So I'm explaining the sequential method now. You open your luggage, let's say you're going to the Caribbean, you put in your flip-flops, your goggles, your swimming trunks, your favorite shirt, and you make an assumption of what you're going to find in your holiday, right? So you go on your holiday, maybe you didn't use all the stuff that you brought with you, but that's your sequential approach. In your concurrent, you're more of an avant-garde traveler, right? You go to the desk at an airport without any luggage, you ask for the first ticket to, let's say, the first airplane, and it takes you somewhere. Without luggage, you go to this destination and you buy the stuff that you need as you go along. Okay? So there are more advantages. As you can see, you've wasted less in the concurrent approach. But when you get to travel back, you just throw away all the stuff that you've bought very wastefully, and you go on your next holiday the next time. So there's a midpoint where we can find something, sort of a hybrid between these two approaches. And this is called adaptive adaptive sequential concurrent methodologies, where going back to my analogy and starting to break down now the analogy, is that you go on your first trip, right, without any luggage, you buy your stuff, and then you send it to your next destination. And when you go to the next destination, you buy more stuff and you put it in your luggage. And so this presents a best of both worlds between these two techniques, which is what we've been developing in our research group. So that was time, connecting models in time. So how do we do this in space? Well, when we speak about a spatial decomposition, the first thing that comes to mind is a domain decomposition. You have a region of your computational domain which is inaccurate, so you need some microscopic model, let's say molecular dynamics, to solve that problem. And in the rest of the region, let's say a CFD simulation is enough to describe the macroscopic problem. So you connect these two within some overlap. A second approach is called the heterogeneous approach, which basically tells you that your CFD is still okay, but it's missing some equations, it's missing some constitutive relations everywhere. So what you do is you resolve at each of these nodes using these microscopic simulations to give you an overview of the missing, let's say, stress-strain relationship within this domain. And finally, we came up with our own niche of applications where we realized that these two methods are still not accurate for solving many of the problems. And so we've realized that there are these high aspect ratio geometries in micro and nanofluid dynamics where we can exploit and even speed up the simulations. So I'd like to show you, I have two stories to tell, two applications to show you with regards to applying these multi-scale methods. So this is a Knudsen pump. It basically contains a capillary, and this Knudsen pump produces a flow without any moving parts. In this particular configuration, I've added two reservoirs because, as I'll show in a minute, there's an experiment linked to this. So the flow is generated not by a pressure gradient, but by a temperature gradient. So if you heat, let's say, the right-hand side of the reservoir and we cool down the left-hand side, then you get a flow happening. And because the size of this capillary is of the order of the mean free path of the gas, then there is a flow happening unconventionally from the cold reservoir to the red reservoir, so from the cold to the hot. And this is a non-equilibrium gas effect that was discovered back in the 19th century, and is called thermal transpiration. So these guys, right, so what will happen in this closed system, as I've shown, is that flow is going to collect in this right reservoir. So the pressures are going to change. So what will happen is you get a flow, a backflow happening to overcome the pressure gradient. So in steady state, what you will have is a flow from left to right next to the surface due to thermal transpiration, and flow from right to left due to the pressure gradient. And this is a steady state flow. So in this process, as I've just explained, there's a transient system happening. And so the question is, what is this transient response? Unfortunately, we've found some experiments who have actually done this in reality, and what they've done is as follows. They started by connecting these two reservoirs, so there's now a feedback loop, so they've equilibrated the pressures. They then have a valve in the middle, which they close, and they let the pressures diverge in time. So why is this problem challenging? Why is it difficult to model? So first of all, we're talking about a problem, so the capillary is beyond the realm of conventional CFD. You cannot solve this with an Navier-Stokes equation. And secondly, the capillary cannot be solved by a particle method because it's very, very expensive. It's quite large, and you need many, many particles and many years to solve that. There's also a multi-scale challenge here. So if we look again, dividing length and time scales, In terms of length, we've got a molecular mean free path of the order of 100 micrometers, all the way up to 3 centimeters of the size of your reservoir. And there's also a timescale separation because you really need to get the collisions correctly, so that takes an order of 100 nanoseconds. And you're trying to track this transient up to a few hundreds of seconds. So what that tells us is that this problem has 5 orders of magnitude in space and 9 orders of magnitude in time to solve. So the way we've solved this is by developing that high aspect ratio method, which we call the internal flow multiscale method. And basically what we do is we treat the most problematic element, which is the IMM, where the non-equilibrium effects happen, and we slice it by applying these individual particle simulations at different slices of our filter. At the moment, these particle simulations feel they're unconnected to the other particle methods. So you need an overlaying method, let's say a conservation of mass and or energy in this case as well. And so now they realize that they're part of a system. So these methods are now going to transfer information. But this is a three-model system. You don't want to be applying any sort of particle method here to resolve this because it's continuum level. So we can use some simple PDE for the conservation of mass within the reservoirs. Now, it's clear to see that these three methods have different time scales that we need to resolve. And so it's natural that we choose time steps for each model to be different. So the particle method wants to make smaller time steps. The continuum method, the one at the top, wants to make really large time steps. And so if you try to make the largest model as the same step as your particle method, the particle method would just tell you, we cannot solve this, it's too computationally expensive anyway. So what we've come up with is an asynchronous time stepping method where we say, provided that the scale separation of the physics is well separated, then we can reduce the time step to something a bit more affordable, but we couple at each and every time step. So this allows us and allows the conservation equation, the PDE, the top one at the top, to fast forward quickly in time and reach the 100 seconds that we want to target, whilst the particle method is in quasi-static equilibrium. So how does the method work? It works really well. These are our predictions. This is not a fit or anything like that. It's just we knew what all the conditions were, and we just decided when the valve was being opened for there. So as you can see, it does really well. But the purpose of these hybrid methods is not just to obtain an accurate solution. It is to also afford computational savings. We're trying to bring this down in terms of a few hours. So what is where do the savings come from? Well, we're using 300 times fewer particles by doing those individual slices. By doing the asynchronous time coupling, we're using 40,000 fewer time steps. And so the overall savings that we get is a multiplication of both space and time savings. And it gives us an order of 10 million times savings than if we had to do this with a full particle simulation. And if you want to know how much it cost us, we used 9 cores for the IMM to give us that solution, and it took 4 hours. And if we had to just solve this capillary only over here with a full particle, it would take 5 million. Of course, we're not running it at the moment. And if you think that was a fluke, we've also run it for all the cases in that paper, and we've got reasonably very good results. Okay, so that was one of the applications and engineering applications I wanted to show you where we applied multiscale methods, and that was for gases. I now want to pivot to liquids, nanoliquid flows. Now the World Health Organization predicts that we currently, 1/7 of our population have a lack of access to fresh drinking water. So it's very important that we come up with technologies to deal with that in the near future. So around 10 years ago, the first experimental paper of water flows through a nanotube emerged, and obviously a few others after that. What I'm showing in this this animation is a carbon nanotube. So the black atoms here are carbon nanotubes. This is a typical molecular dynamic simulations which we run in our group. And it's not very clear, but on this side you would have the liquid which you want to filter out. So these green and yellow atoms are, let's say, the ions. But it could be anything. It could be bacteria or any other elements you want to filter out. And so the prediction is that we would like to make a membrane of all these aligned nanotubes, which are so small, they are 1 nanometer roughly in diameter, that the water, which is a relatively small atom, just slides through the nanotube, leaving all the other particles, the larger particles, in the feed end of your system. So now what we're seeing is just a glide route to the nanotube, just to show you the scale at which we're talking about. These are individual water molecules. So when I teach fluid mechanics to in engineering in Edinburgh, I teach them the Hagen-Poiseuille flow equation, which is this one over here. And it explains, given a pipe length and diameter and so on, and the pressure gradient, this is the flow rate that you expect. Now if we scale that pipe down to a diameter which is of the order of 1 nanometer, and we observe what that flow rate is, let's say m dot over here. So if I define a ratio which is the observed flow rate over what the expected in theory, then I get this flow enhancement ratio E. So if E is 1, then our theory predicts everything is great. But if E is much more than 1, then we're seeing some flow enhancement in our system. And what I've put in the table on the right is a series of experimental data for very similar nanotube diameters, and the fourth one is the flow enhancement. So it's not 1, it's 1,000, almost 100,000, 400,000 times. So we are, for a smaller system, we're expecting 400,000 times or less flow passing through our tube. And that's great. That was a very interesting research outcome in the 2005 region, 2006. And it sort of sparked the research area which said, okay, we're probably going to use, this is a great technology, we're going to use less energy, we're going to get more flow out, and so on. Obviously there are more challenges than that. So we decided to model this. We were the first to model a multiscale simulation of this. And again, the reason why this is so challenging is if you take just one of these nanotubes that we're trying to solve in a membrane, the CFD doesn't apply because we have all this non-continuum effects, like the ordering of the molecules, for example. These are the sort of nanotubes we're talking about perfect rejection. And you can see, if we look at the density, it's 4 times that what we expect in the bulk. And there's also this ordering that cannot be captured by a CFD simulation. And this one tube to do this with molecular dynamics would require hundreds of years to solve. So how do we solve this problem? So we came up with 3 multiscale methods, and I didn't want to go into too much detail, but I'd like to sort of overview of what we've done. The first method, we said, let's apply CFD simulation, right? We tried to run sequential pre-simulation, so we run some MP, understand what all the physics is, and try to enhance and tweak the Navier-Stokes equations as much as we can in order to try and compare with our benchmark case, which was a full MD simulation. And no matter how much we tried, no matter how much we tweaked, we never managed to get as close as less than 30% accuracy with the Navier-Stokes. So we brushed this aside and moved on to two more methods. The second method is the concurrent method. I've explained what concurrent simulation is, where you have DMD running concurrently with some one-dimensional equation. And we found it was great. I'll show you some results in a second. We found it was great for really short nanotubes, but when we started making them long, when we tried to come close to experimental thicknesses, we found that it was too noisy. So the MD has an issue with statistical noise that doesn't allow you to resolve flows. The third approach was that adaptive method I was talking to you about. It's not there's no machine learning. This was just done by a postdoc, essentially myself, a few years ago. And basically what we've done is we've run one concurrent method, we've learned what has happened, and so we've rearranged or reconfigured the problem into flow resistances. So we've understood what the flow resistances are in the problem, and by understanding what the flow resistance is, we can make predictions for any length we want, and that's all. Okay, so these are, what I'm showing in this graph is, the y-axis is that flow enhancement factor I described, which is how much more flow you get through the tube. And the bottom one is the thickness of the membrane. So these are all experiments, and when we started compiling this assignment, we started worrying about why these are so dispersed, and it's in fact what's driven us to do these multiscale simulations. So with MD you can only sort of arrive somewhere here, and so we wanted to see how our multiscale methods fare. Okay, so the first thing we did was we ran full MD simulations. So these are easily done on a computer. These were done on a high-performance computer. And I've heard this one from ETH Zurich took all the processors on their supercomputer to solve that particular point. And it spent maybe 3 months doing that point over there. But we wanted to do better than that. So the concurrent method, which I've explained previously, this was our second method, was able to show agreement with our full MD, but also to take us a bit beyond. I want you to know that this is a log scale. So we went a bit beyond, and we realized that we're getting into a noisy period, and we stopped over there. So our adaptive method is the best. We were able to learn from just a couple of concurrent simulations what those flow resistance were, and we were able to make predictions for this particular nanotube diameter. We didn't stop there. These simulations took a couple of weeks, so we went for all the diameters we could possibly do, and here I'm showing just a few of those. And we now started to realize which experimental results sort of agreed with our simulations and which ones didn't. So just pointing a few out, this is a diameter of 1.6. This is our 1.6, so we're not so far off. This is 3 nanometers, this is our 3 nanometer diameter, so we're still not far off. And these results are the same trend we see here, but they're slightly downwards. We have no idea what's going on here. There might be some other physics. To this day, no one has explained why those are so large. Our predictions for other diameters indicated that should be somewhere down. So that was what we've done for multiscale flows in carbon nanotubes for filtration applications. However, we've applied this to many other problems. We are also applying this to current problems, such as we're in collaboration with Nokia Bell Labs, who are interested in cooling the next generation processors using similar membranes, but the physics is completely different. We want to use evaporative cooling to solve this problem. We've worked in the past with reaction engines to do these high altitude space planes for their top secret micro heat exchangers. We're working with King Fahd University of Petroleum Minerals to solve the shale gas problem, which is how do you go from a molecular surface up to a reservoir, which is 10 kilometers wide. We've done some drag reduction multiscale simulations for AkzoNobel, and we're also working with Nokia to do these droplets in cooling devices. So in conclusion, I hope I've given you a taste of what we've been working on with Jason led when he was a professor in Edinburgh and Strathclyde. We've developed a wide variety of these hybrid models to deal with multi-scale flows, starting from micronano up to macro scale. And what I've shown you in this talk is two applications, one of quantum pump and one of filtration. And we've shown that by using various methods, you can actually come up to 10,000 million savings by doing this. So there's an opportunity here to do these or incorporate these methods in your research as well. And finally, it's very important that we make that bridge into industry, and that's what we've been working on. We are now sort of transferring this knowledge to industry. They are using our software to design things like sort of lithography machines and these membranes and so on. So I'd like to thank you guys for listening, and I'd like to thank Jason in particular and all the staff and researchers and funders that made this research possible. Thank you.
A couple of minutes for questions. Any questions?
Hi, the great presentation, very interesting stuff I've never heard of before. The comparison with the experimental data that showed very large errors in the experiments. What was the cause of those?
You mean this one? So this is their spread of results. It indicates their spread, right? So they've carried out the same experiment over and over again, and they got a different result. So there's a spread of.
Do you know why it was different?
I would say that these nanotubes are so small that you don't know what's going on in there, right? We're talking about 3 nanometers.
So it was damaged them?
They could, yes. Sometimes they do sort of Raman spectroscopy afterwards to see the amount of damage that they do to the surface.
Further questions? Take one question.
The multiscale approach sounds very promising. Do you use it in commercial software, or do you write your own code?
So we write our software in OpenFlow.
Okay.
So we work really closely with OpenCFD who transfer this code. So some of our codes are already available in OpenFlow. We're also working with with Darsbury Laboratories who are helping us with MUI, which is a sort of interface software that can handle anything from any MD simulation to a CFD simulation.
Okay.
So we've got, I can send you links to these GitHub accounts.
Okay. You don't happen to work with commercial software as RCCM and our experience with multiscale approach can be applied there?
No.
Okay. Thank you.
It's good. Thanks a lot, Michael. Thank you.